Aqueous solutions. So when we talk about an aqueous solution, we mean that something is dissolved in water. That's what aqueous means. A solution is a homogeneous mixture. When ionic compounds dissolve in water, they generally dissociate into their component ions. So you put sodium chloride in water, and the sodium ions and the chloride ions go their separate ways, and they form a solution. And they mix thoroughly, and that's why it's homogeneous. So here's an illustration of sodium chloride dissolved in water. We have the sodium ions, we've got the chloride ions. They mix completely with the water, the top of the water, the middle of the water, the bottom of the water. It's all just as salty. There's no oily layer, there's no clumps at the bottom. It's homogeneous. We've talked about that. The ions dissolve, they dissociate. Dissociate means that they're going apart from each other as opposed to associating. They're dissociating from each other completely. And so we don't have any sodium chloride units or sodium chloride molecules present. It's all sodium ions and chloride ions. And when we have substances like this that dissociate into ions completely, we call these strong electrolytes. They're strong electrolytes because they conduct electric current strongly. So here's an illustration. Here we have a glass of water, a battery, and a light bulb. Now, if we touched these two electrodes, if we connected those, the battery, the electricity from the battery would flow through the light bulb and the light would go on. The light's not going on here because these two electrodes are immersed in pure water. Pure water does not conduct electricity well. You might say, well, what about lightning? Yeah, well, lightning is so much voltage that almost anything, there's limits. But pure water, low voltage, not going to happen. If we throw some salt into that water, the light bulb will go on. Because the salt dissolves in the water, forming sodium ions and chloride ions. Electric current is the flow of electrons. The electrons need a way to get from one electrode to the other. If they're not touching, they can't jump through space. And so what happens is you get these charged ions are able to carry the electrons from one side to the other, kind of like a ferry boat or something. The ions conduct electricity, causing the light bulb to light up. So these are called strong electrolytes because you put a strong electrolyte in the water and the light bulb glows strongly. There are also weak electrolytes. You put those in the water and you'll just get a weak glow. We'll talk more about that later. Yes?
So when people say you need electrolytes, like after you work out or whatever, that's when...
This is related to electrolytes, yeah. So, they say, well, you were sweating a lot, you need to replenish your electrolytes. Electrolytes are ionic compounds that are soluble in water, and your body needs a certain amount of sodium and potassium and chloride because there are electrical processes that go on in your body. And when you sweat, you lose a lot of those ions and you need to get them back. And so electrolyte, as used in like a Gatorade commercial, does actually mean the same thing as electrolyte used talking about dissolving ionic compounds. It's a good question. Yes?
So is it that sodium chloride is one of the strongest of these strong electrolyte solutions? Or is there...
No, there are a lot of strong electrolytes. And what it means is they dissolve completely. So there's strong electrolytes, and there's not really a variation in how strong they are. The weak electrolytes, there's, kind of a range of strengths. But
So does that mean, like, if you were to take Gatorade and do this...
if you put Gatorade in water, the light bulb would go on. If you put Kool-Aid in the water, the light bulb would not go on. Because sugar is not an electrolyte. Sugar doesn't ionize, and it doesn't conduct electricity. It dissolves in water, but it doesn't conduct electricity. A strong electrolyte dissolves, forming ions. It is interesting.
Okay.
Yes?
Okay, so we talk about, these flash bombs that take the electrical out of all of our devices.
Okay.
I don't know what the terminology is, the devices that take all the energy, I mean, it's like the demise, that they're able to do that with a certain type of bomb, or a certain electromagnetic.
Yeah, it's like an EMF or something, electromagnetic
takes
force.
all the
The
energy.
bomb, and it just like destroys
Right, wipes out
everything
all-
electrical.
Right. So if we were to, like, survival-wise, need some type of lighting, would we still be able to, would the chargers and batteries still be enough to do something in that order where we could just take, say, water and salt?
I am not. I've heard of those devices and phenomena like that. I am not sure exactly how they work. I do know that, like with electricity striking a building, if your computer is plugged into the wall and your house gets struck by electricity, your computer's toast because the electricity will go through the wires in the house. If the computer is not plugged in, there's a reasonable chance that it will not be affected at all.
So the same effect possibly with batteries, that if they're not.
Right, if you just have batteries sitting somewhere and you had one of those EMF bombs, I'm not really sure if that would affect those or not.
Just remember that. Well, no, I mean, it's a
Well-
survival, I mean, look at how easy that is.
Exactly, and I think that it's good.
No, but
I think it's
it
good.
made me think of, it just made me think of that because how
Right.
easy that is. It's such a simple, but yet.
Well, and you can actually make batteries out of everyday stuff.
Right.
You
I
can make
understand
a
that
battery
also,
out of
yeah.
a potato. You know, there's various things because, yes, you could destroy electrical equipment. Can you destroy nature to the extent that you could not remake those things? No. No, you can't.
Right, because they have their own energies.
You could take all the ions and turn them into elements, but then those elements are going to want to react and form ions again. And so something like that is not nuclear, and it's not going to actually destroy the atoms. So that's interesting to think about. And I think the more you know about chemistry and physics and biology, the more you're able to understand some of these things. Very interesting question. So let's look at silver nitrate dissolving in water. Now, silver nitrate has a polyatomic ion, nitrate. When silver nitrate dissolves, it is also a strong electrolyte. The silver ions and the nitrate ions separate, but the nitrate ions stay intact. They're a polyatomic ion. It's like that bundle pack from Costco. It stays intact. It's shrink wrapped together. Okay? So when we looked at nomenclature, we identified that there were two ions. And when that dissolves in water, it dissolves into the two ions. There are compounds that have more than two ions, but we're not going to talk about them in this class. Okay? So everything we're going to encounter, two ions. So you've got the positive ion and the negative ion. So the silver nitrate, you get silver ions and nitrate ions. The polyatomic ions dissolve as intact units. Silver chloride does not dissolve in water. Not all ionic compounds are soluble. Some of them are, some of them are not. You put sodium chloride in water and you can stir it all day long and it's just going to sit there as a lump on the bottom. It's not going to dissolve. So we would call this a non-electrolyte. It's not an electrolyte. How do we know if something's going to dissolve in water or not? We say a compound is soluble if it dissolves in that liquid. And we're pretty much only going to talk about water, but things can be soluble in other liquids as well. A compound is insoluble if it doesn't dissolve. The way that we predict the solubility of ionic compounds is through a set of rules. These are empirical rules. They were developed through observation. You know, you take sodium chloride and you put it in water and you stir it up. Yep, that one dissolves. Okay, let's try potassium chloride. Let's try this one. Let's try that one. And they just tried them all. And then looked at patterns and made up a set of rules. So this is how your book presents the solubility rules. And I'm not going to make you memorize this or write it on your 3x5 card. I will give you this when you need it on an exam. So these compounds in this first table, first portion, these are mostly soluble. And then over here they list exceptions. So lithium, sodium, potassium, ammonium. Compounds containing those ions are generally soluble, no exceptions. Compounds containing nitrate and acetate ions are soluble, no exceptions. They really should have lines on this table. Chloride, bromide, iodide, mostly soluble, except if you have any of those ions pairing with silver, mercury 1, or lead 2, then it's insoluble. Sulfate compounds are soluble, except with strontium, barium, lead, or calcium. So if you have calcium sulfate, not soluble. Sodium sulfate is soluble. So those are the ones that are mostly soluble. These are insoluble with some exceptions. So hydroxides and sulfides are generally insoluble, except if you've got either of those with lithium, sodium, potassium, or ammonium, it's soluble. And that's needed because we can't have this not be true. If you've got sulfide with calcium, strontium, or barium, it's soluble. If you've got hydroxide with calcium, strontium, or barium, it's slightly soluble. What does slightly soluble means? Well, it means a little bit dissolves. So we're generally going to need to break this into two groups, soluble and insoluble. Slightly soluble, we're going to lump in with the insoluble. A little bit dissolves, but it's mostly insoluble. And then we've got carbonate and phosphate, and those types of compounds are insoluble except with lithium, sodium, potassium, or ammonium. So we need to learn how to use this table. So determine whether each compound is soluble or insoluble. So the first one is copper sulfide. Well, we have to go look at the table. And we're looking for copper and sulfide in the table. Start at the top. We don't see copper or sulfide. That's sulfate, but that's not the same. Here we go with sulfide, S2 minus. So mostly insoluble except lithium, sodium, potassium, ammonium. I'm looking for copper. Calcium is a lot like copper, but it's not copper. Calcium, strontium, barium. Okay, so I don't see copper sulfide as being an exception. So copper sulfide is insoluble. Insoluble. If you put copper sulfide in water, not going to dissolve. Let's do another one, FeSO4. Well, we're looking for iron and sulfate. Well, here we've got sulfate. Sulfate compounds are mostly soluble. Let's check the exceptions. Do we see iron in there? No. Iron is not one of the exceptions. So iron sulfate is soluble. What? It doesn't like when I switch back and forth, so we'll just have to get over it. So this one is soluble. Lead carbonate. Again, I go back and look. So we're looking here for lead or carbonate. We're not seeing those, not here. Oh, there's carbonate. Carbonate is generally insoluble. Let's check and make sure there's no exception. Lead is not listed as an exception. So PbCO3 is insoluble. insoluble. You following how this is working? The last one, NH4Cl. This is that weird kind of ionic compound that doesn't have a metal in it. Ammonium ion and chloride ion. So we go up here, lithium, sodium. Oh, there's ammonium, NH4. Mostly soluble, no exceptions. We can stop looking. So ammonium chloride is soluble. So I'm not going to make you memorize the table or write it on your 3x5 card, but you need to know how to use it. Any questions?